We're going to finish off our relativity notes with something called length contraction. And we have a spaceship traveling from Earth to the nearest star, which is 4 light years away, at a speed of 0.9 c relative to Earth. So if it was moving at the speed of light, it would take 4 years to get 4 light years. So it's going to be a little bit over that. And we're going to do velocity is distance divided by time. So 0.9 equals 4 divided by time. Cross multiply and we get time is 4 divided by 0.9, which is 4.4 years. So a little bit over 4 years, which is what we thought. Now that's from someone from Earth who is at rest. The traveler traveling in a spaceship is going to have a shorter time because time goes slower for him. And in the last set of notes, we had this equation for that. So we're going to figure out the time that he thinks it takes. So for someone on Earth, it was 4.4 years. And when we solve that, we're going to get that his time is 1.94 years. So it seemed to him to take less time than to the person who was at rest. And that's the way it should work. The person who's moving, the time ends up being shorter. Now, the distance of the star from the perspective of the traveler. So for him, what he really sees is the Earth is here and the star is here. He's at rest from his perspective, and the star and the Earth are moving with a velocity of 0.9. So we can use the same equation. Velocity is distance divided by time. And basically it's saying how far will the star move to get to him. And we get the velocity is 0.9. And the distance is what we're looking for, but his time was 1.94 years. And maybe I'm going to call that one d prime, because that's what he perceived it to be. When I solve this, I'm going to get a distance of 1.75 light years. So quite a bit shorter. So what we found is that the time is shorter for the person who's moving, and the distance is shorter. So length contraction. The length of any object moving relative to an observer will be shorter or contracted. And the equation is going to be very similar to what we had for the time. And this length is called the proper length. And that's the length when it's at rest. All right, so we have an example problem here for this. We have two identical spaceships. Each one's 100 meters long. So if they're at rest, if they're both at rest, Starship A is 100 long. And B is 100 meters long. Now from the perspective of ship A, what is the length of each ship? Well, for him, the velocity of the ship is 0. It's at rest. And ship B is moving with a velocity of 0.8 c. So the length of this ship, he's just going to say, is 100 meters. But because B is moving, it's going to seem shorter. So we're going to say L prime is L square root 1 minus B squared over C squared. So 100 was the length of this when it wasn't moving. Square root of 1 minus 0.8 squared. And I'm going to end up with 60 meters for this one. Okay, so observer A says that his ship is 100 meters long, and ship B is only 60 meters long. But for the perspective of ship B, he would say he's at rest. And the length of the ship is 100 meters. And to him, A is moving back this way with a velocity of 0.8 c. Then we want to know the length of it. And it's going to end up actually just being the same math. And we're going to end up with the length of 60 meters. So this is going to be 60 meters long. So in this case, A says my ship is 100 and B's is only 60. But B says, no, mine's 100 and yours is 60. And who is right? And it turns out they're both right. In their reference frames, which basically means from their point of view, the other ship is moving and therefore shorter.